Yes, pretend that never happened. Okay. So we're going to be covering, why is this not working? Modular arithmetic. We'll be skipping over the basics and assume that everyone knows that's. Okay. So first off, we're going to start with the Chinese remainder theorem. So if we have relatively prime integers n1, n2, n3, so on to nk, and the integers ak. Then if we're given the system of equations, x is congruent to a1 mod n1, a2 mod n2, so on to x is congruent to ak mod nk. Then we claim that x has a unique solution mod, or basically x is uniquely defined mod n1, n2, n3 to nk. Will be mostly considered a case where k equals to 2 because we can generalize from there. So let's say we have x is congruent to a mod n and x is congruent to b mod m. And then m and n are relatively prime. Now we want to prove there exists a unique solution mod mn. Okay. Well, we first prove this is unique, right? Let's get a general overview first. For example, we can let x equal to 1 mod 5 and 2 mod 3 or something like that, right? Then from here we get x is congruent to 1, 6, or 11 mod 15. And we confirm in this case there is an x that's congruent to 2 mod 3, and that's 11. So we first prove the solution is unique, right? Because if we were to have like two different solutions, like x and y mod mn, then this will apply x is congruent to y is congruent to a mod n, and x is congruent to y is congruent to b mod n. So then we get m divides x minus y, and n divides x minus y. And since they're relatively prime, this implies that Mn divides x minus y. So then x congruent to y, mod Mn. So we see it's unique. Okay. And now we kind of prove that for this solution exists. That's the easiest way we can like see this, that there exists, is if we consider n by n grid, right? With like all the modules one. In this class, to save time, we'll only be covering the ideas behind the proofs, and the more detailed proofs will be in the handout. Well, we noticed that that like each like mod Mn, like 1, 2, 3, all the way to Mn, right? These numbers are going to be in this grid here. For example, we have that, right? So we can keep filling out the grid. And then we see such as there's Mn spaces and Mn numbers, and then two numbers can't go into one space. Each row and column must have one number. And that number is the solution. For example, if we consider a 3 by 4, oops. Whatever. I think I did this wrong. Whoops. Okay, 3. Okay, there. Right? We see that there's one number in each cell. So the one solution for each, and there's and everyone has a unique one. Okay. Okay, now I have Bézard's lemma. This is also called Bézard's identity. Oh, the numbers in the chart, okay. So basically this is mod 3, this is example, right? The numbers are mod 12. For example, we have 1 here is 1 mod 4, 1 mod 3, right? 11 is 3 mod 4 and 2 mod 3. So this is just an example. In the general case here, we can prove that there exists one number each spot because like no spot can contain two numbers, and there's the same number of spots as there are numbers. So if we have a system of equations like this with congruences, there is a unique solution on Mn. This is also okay. So now we move on. So if we have integers a and b, and d is the GCD of a and b, then we claim that there exists integers x, y such that ax plus by is equal to d. Now we can simplify this because we can let a equal to a1d and b equal to b1d. And then the greatest common factor of a1 and b1 is 1. So basically, this is the same as if a1 if a and b are relatively prime, then there exists a solution to ax plus by equals to 1. Okay, we can prove this. So first we claim that there exists an x such that ax is congruent to 1 mod b. Okay. We can see this is true because if we consider 1a, 2a, 3a, all the way to ab, there's b numbers here. And also b residues mod b, right? So unless two of these things are equal or congruent, there will exist some number x such that ax is congruent to 1 mod b. So let's say there are two things that are such as that's equal. So for example, ax is congruent to a1 is congruent 1 mod b. To congruent mod b, we don't know what it is. In this case, we have ax minus y is congruent to 0 mod b, which since a and b are relatively prime, this means that b divides x minus y, which implies that x is congruent to y. So therefore, these b values are distinct. So there must be some value such that this is true. Then we can write this as ax equals to 1 minus by for some integer y. So then ax plus by equals to 1 has solutions in integers. Does anyone have questions? If not, we'll move on. Now I'll go to some multiplication. So we have, once again, if the GCD of A and N are 1, or they're relatively prime, then we say there exists B such that AB is congruent to 1 mod N. We call this number the inverse of A. We can also write this as to the -1, like that. Note that this is not equal to 1 over A in terms of mods, because you can't have fractions. So when dealing with mods, we don't divide. If you want to divide, you multiply by the inverse. Okay, from before we see that that this number must exist. B must exist if A and N are relatively prime by the same logic as before. Now we consider if the A and N they're not relatively prime. In this case, we see that an inverse doesn't exist. For example, if we have A equals to 2 and N equals 4, right? We cannot have some number such that this is congruent to 1 mod 4, because this is even and this must be odd. In the general case, we see that this is divisible by the greatest common factor. And this is also divisible by the greatest common factor. Not divisible. Right? Because this is, in this case, because we see that N is divisible, so 1 mod N cannot be. Okay. And then lastly, we want to show that the inverse is distinct. Because we want to show that this is distinct, right? It cannot equal to, so for example, we cannot have A and C such that they're both congruent to 1 mod N, and B is not congruent to C. We want to see this is false, right? Well, if we do have them, then AB is congruent to AC mod N, which implies that A times B minus C is congruent to 0 mod N. Once again, since A and N are relatively prime, this implies N divides BC, which then contradicts with that. So the inverse is unique. Does anyone have questions? Okay, we'll move on. We have Wilson's theorem. So basically, for some prime P, what do I mean by the inverse is unique? Well, unique mod N. For example, there only exists one residue. There is one residue mod N such that A B is congruent to 1 mod N if they're relatively prime. For example, you cannot have two B's. B is uniquely determined by A. Okay. Does that answer your question? Okay. So we have some prime P. Then we claim that P minus 1 factorial is congruent to -1 mod P. P minus 1 factorial here is P minus 1 times P minus 2 times all the way to 3 times 2. Okay, let's see why this is true. Oh, maybe we want to try some. Let's try to convince ourselves this is true by considering a small case. Let's say P equals to 5. Then 4 factorial is congruent to 24, which is congruent to -1 mod 5. Right? Okay. So now we have a general case. So we pair these numbers off. We pair numbers such A and B such that they're multiplied to 1. So we pair the numbers with their inverses, right? For example, if we have, consider P equals to 7, right? So we can pair 2 with 4 and 3 with 5. And we're left with the numbers such that where A is equal to its own inverse, or basically A squared is congruent to 1 mod P. So we have A is equal to P minus 1, or A is equal to 1. So we're left with these two numbers. And everything else pairs with a number. So we can pair these P minus 3 numbers with their inverses. So we're left with P minus 1 times like a bunch of numbers that pair to 1, right? So this becomes that. So this is just congruent to -1 mod P. Does anyone have questions? P minus 2 factorial, it's 1. Actually, we'll see that in our next example. Example. So we want the remainder when 71 factorial is divided by 73. Right? Then, because we note that 72 factorial is congruent to -1 mod 73, because 73 is prime. Then this means that 72 times 71 factorial is congruent to -1 mod 73. And 72 is just -1 mod 73. So if we multiply both sides by -1, we see that 71 factorial is congruent to 1 mod 73. Or we can just generalize this to P minus 2 factorial is congruent to 1 mod P, as someone mentioned in the chat. Any questions? Okay, then we'll move on. Formats. So if we have A is relatively prime to P, and P is prime, I probably should have specified this in the handout, P has to be prime. Then A to the power of P minus 1 is congruent to 1 mod P. Okay, let me prove this. We consider numbers A, 2A, 3A, all the way to P minus 1A. Right? We know this is some permutation of 1, 2, 3, P minus 1 mod P, right? Because as we showed before, none of these things are equal. So then A times 2A times 3A times all the way to P minus 1A is congruent to P minus 1 factorial times A to the P minus 1 power mod P. But we can also replace this with 1 times 2 times 3 times P minus 1 which is P minus 1 factorial mod P. This is just -1. This is also just -1. Then, since these two expressions are congruent, A to the P minus 1 has to be congruent to 1 mod P. Does anyone have questions? Okay, we'll move on. I have an example. We want the remainder when 2020 to the 2020th power is divided by 41. Well, we first note that 2020 is congruent to 11 mod 41. And also 11 is relatively prime to 41, so 11 to the 40th power is congruent to 1 mod 41. So then 20, this is congruent to 11 to the 2020. And we can split this into 11 to the 20 times 11 to the 2000. This is congruent to right. So this is just 1. So we have 11 to the 20. This is congruent to well, we can make this as 121 to the 10th power. And 121 just negative 2 mod 41, so this is negative 2 to the 10th power, which is 124, which is congruent to 40 mod 41. Does anyone have questions? Okay, moving on. So now we define the Totient function. So we define the Totient of N. This is a number of positive integers less than N that are relatively prime to N. So we claim that if N is P1 to the E1 times P2 to the E2 times PK to the EK, where the P's are, these are prime numbers, and these are positive integers, then the Totient of N is equal to N times P1 minus 1 over P1, P2 minus 1 over P2, all the way to PK minus 1 over PK. We get a general intuition of this formula because, well, this many of the numbers are going to be relatively prime to P1. Then we have this many numbers relatively prime to, like, this fraction of the numbers are relatively prime to P2, and so on. This gives us a general intuition as this formula is correct. But of course we're going to have to, of course we're going to prove it. First we notice that if we have P to the M for some M, right? Then the only numbers not relatively prime are P, 2P, 3P, basically all the multiples of P. Right? Now there's P to the M minus 1 numbers less than this, and then P to the M minus 1 numbers that are not relatively prime. So then there's P to the M minus P to the M minus 1 numbers that are relatively prime, or basically a totient of P to the M is P to the M times minus P to M minus 1, or this is P to the M times P minus 1 over P. Okay, now we claim that the totient of AB is equal to totient links to the first two classes. Wait a moment. Here are all the files. Only the for recordings, only the geo recording still up there. But you have access to all the handouts and problems. Okay, we claim that the totient of AB is equal to totient of A times the totient of B if A and B are relatively prime. This follows from a Chinese remainder theorem, since if N is congruent to, let's say, something relatively prime. So basically, if we have some N that's relatively prime, right? We consider so these N's are basically residues modular AB, right? And each N splits into let's call them C and D mod A, since A and B are relatively prime, right? So basically for each C and D relatively prime to A and B, it generates an N relatively prime to A and B. So the number of ways we can count that these C and D is the number of C's is the totient of A, the number of D's is the totient of B. So the number of N's relatively prime to A and B is a product of them. So then the totient of N we can write the totient of N as this. Like this is the prime factorization of N. Now this is just N. And then we're left with these. Does anyone have any questions? Okay. What? Okay. So we'll have an example. This example is from a few classes ago, so it might look familiar. But now we're going to do it a different way. So we want positive integers less than 60 that are multiples of 2, 3, or 5. Less than or equal. Okay. So first we notice that these are the only prime factors of 60. So the only numbers that are not multiples are the ones relatively prime to 60. And since the numbers have to be less than or equal to 60, this is a totient of 60, which is equal to 60 times. This is 16. So these are not multiples. So then the multiples of 2, 3, or 5 less than or equal to 60 is 60 minus 16, which is 44. Does anyone have questions? Okay, then moving on. We're running out of time. Now we're going to generalize Fermat's little theorem, and this is Euler's Totient theorem. So again, if A is relatively prime to N, what do you mean by the other way around? The last problem had a totient of 60 is oh, and for a totient, this is a generalization of Fermat's because it's more general. Fermat's is more specific because totient covers all integers n, while for Fermat's you want n to be prime. Okay, we'll just quickly go over the proof. So we consider just huge list of numbers that are relatively prime to n. Like all the residues relatively prime to n. And then let's pick some residue A. Then we have this is a, since A1 AI is not congruent to AJ cannot be, right? We know that A1, A2, A totient of N, right? So basically A times each of the numbers in this list. This is some permutation of it. We can define this product as B. Then B is congruent to this product, which is A to the totient of N times B. And since we know these numbers are relatively prime to N, B is relatively prime to N, so we can multiply the inverse of B. So the A to the totient is congruent to 1 mod N. Does anyone have questions? Okay. Let's go here. Okay, we have another quick example. So we're going to, yeah, N can be anything. N can be anything. Example. We want the remainder of 2020 to the 20th powers divided by 90. I mean 39. Okay. So we know the totient of 39 is 39 times 2/3 times 12/13, and this is 24. We have 2020 is congruent to 31 mod 39. So, and since this is relatively prime, 31 to the 24th is congruent to 1 mod 39. Then 2020 to the 2020 power is congruent to 31 to the 4th power times 31 to the 24th to the 84th power. We basically split 2020. And this is just 31 to the 4th. To make calculations easier, we can replace 31 with -8, because that's congruent to 4th. So this is 64 squared, which is congruent to 25 squared, which is 625, which is congruent to 1 mod 39. Does anyone have any questions? If no one has any questions, I'll split you into breakout rooms so we can work on problems together. The problems are in the handout, which I'll send in the folder, which I'll send one more time.